Hello again, and we're going to be off and running on to some new and amazing stuff that deals with differentiability. Differentiability is basically what points can you find the derivative of the function. There are points that you can, and there are points that you can't. So we're going to have to take a look at when our function's differentiable. But before we do that, we're going to kind of do a quick review of what continuity is. And we're going to take a look at some parent functions, and you need to know which parent functions are continuous on their domain. So the first thing I'm going to do is I'm going to present to you my screen, and I'll share this with you. And you should see on the screen there, you should see differentiability and continuity. Okay, so what we're going to do is we're going to talk about parent functions first and their continuity. Now, before we even get started, we need to talk about one thing. What does it mean to be continuous on its domain? Okay? These are words that we're going to see very often in calculus, okay? Continuous on its domain. What does that exactly mean? Well, first of all, let's just review what domain is. Domain is all x values that have a f of x or y value. Okay, that's the most important thing that you need to know. It's every x value that does have some f of x value or y value. Now remember, sometimes it can be undefined, and we've talked before about those points that are undefined. So to be continuous on its domain, the first thing you do have to look at for every function, so the first thing you look at is the domain, and you need to define it. So yesterday I handed out to you a parent function graph. So what we're going to do is we're going to do a little bit of work on that parent function graph. So take this out, and you should see it says C.2.2, 12 parent functions and their graphs. So the first thing we're going to do is we're just going to kind of look at the first row, and we're going to just talk about what is its domain. Okay? So if we take a look at this first one, you'll notice, and I'm going to just use the letter D, every x value, as we go this way, has a corresponding y value that hits the graph. Same thing with this one. Every x value that goes this way, it hits the y value. There is a y value. So this domain is all reals. Okay, so we use that kind of double-legged R to represent all reals. Okay, so let's look at the next one. This is a quadratic. So if you remember, this is linear. This one is a quadratic. And also, if you look at it, its domain, again, is as you go this way, every x value has a y value. So its domain is also all reals. So we're going to keep going through, and we're going to look at all of these different things. I'm just going to zoom in a little bit just to kind of help you see that. There we go. So these are the functions that we're working with. Now, the next one is called a cubic. And you'll also notice that as we go to all these x values, then there is a corresponding y value, whether you're going positive or negative. So its domain is also all reals. Okay? So what I'd like you to do is I just would like you to look at the sheet right now, pause your video, and just find all of the functions that have a domain of all reals. Okay? So pause the video, and go through and look at all of the functions that have a domain of all reals. Now, if we quickly look at these, it's going to be domain is all reals. The domain here is all reals. Okay. This, of course, is an absolute value. Okay. This is, of course, a sine function. This has a domain of all reals. Cosine function, domain of all reals. Okay. The x to the 2/3 has a domain of all reals. Okay. This is the circle. Okay. So if we take a look at the equation of a circle, depending on the size of the circle, I guess it could be all reals, but this one does not at this point. This one, just looking at the graph, this has a domain of all reals. This one down here has a domain of all reals. Okay, you can cancel that one out. And then this one also, surprisingly, has a domain of all reals. Now, let's take a look at one that does not. Okay, so let's go back to the top and take a look at this function right here. This is, of course, a square root function. Okay, now take a look at its domain. We know something about square roots, and square roots can't have values that are in the negative area. So if we take a look here, just looking at this parent function, the domain of this one is x has to be greater than 0 or equal to 0. Okay? We can also write it as it can go down to 0 and then up to positive infinity. So we can write those either way. Okay? So it is all numbers greater than 0, or it's the numbers between 0 and positive infinity. The same thing goes for the natural log function. The natural log function, though, is a little bit different. It's all values greater than 0, but it can't be equal to 0. You notice that it kind of has an asymptote there. So we would use parentheses 0 and then to positive infinity. Okay? Now, this, of course, is the e function. Okay? This one, though, is 1 over x. Okay? 1 over x is a reciprocal function. This function, you'll notice, has values everywhere except right here. Okay? So we can say the domain is all reals except x cannot equal 0. The same thing holds true for the x squared function. The domain is all reals except x cannot equal 0. Now, the other one that has this is this one down here. This is the absolute value divided by x. This has a domain of x is where it's all reals except x cannot equal 0. Because remember, you cannot divide by a 0. So are you kind of getting the feel for this? Looking at a graph, all of these functions have very specific domains. Now, this comes into play when we start talking about continuity. Okay? So let's talk about something. Let's take a look at what does it mean to be continuous. Continuous on its domain. What that means is you need to look only where the domain is, not its exceptions. Okay? So let's look at this linear function. So let's go back to our linear function. Now let's talk about the linear function itself. Is that one continuous on its domain? Well, its domain is all reals. So looking at all reals, is there any spot where you would say it's not continuous? Okay, so this function then is continuous on its domain. What would you say about the quadratic? Well, its domain is all reals. So looking at all reals, is there any spot where the quadratic function has a gap, a hole of some sort, a jump, or a vertical asymptote? Okay, nope. So this is continuous as well. Now, let's start just kind of looking at them. So only look at its domain. So this is all reals. This one is also continuous on its domain. So is the next one. Now, take a look at the square root function. Now, this is where everyone starts to think and go, okay, is this continuous on its domain? Okay, well, its domain is all numbers greater than 0. Okay, so is it continuous in its domain section? Okay, and if you notice, all the way through here, there are no gaps, there are no holes, there are no vertical asymptotes. So on its domain, it is continuous. Okay, now at this far end, we have other things going on, but as a whole, if you just look at its domain, it's continuous. This is also continuous on its domain. Even though there's an asymptote, everywhere above 0, the graph is one continuous straight line. Okay? This one is also continuous on its domain. Has we run into this little bad boy over here, and it's 1 over x. It's a reciprocal function. We know that it has a vertical asymptote at 0. Now, we defined its domain as all reals except x cannot be 0. So we exclude that completely. Looking at just the sections where x is not 0, is it continuous on its domain? Well, in this case, it is continuous on its domain. Okay? Excluding 0, it's continuous everywhere else. So if you kind of get the idea, we exclude those things that are not in its domain, and we look at every other part of the graph. So this one is also continuous. This one is also continuous. So is a sine function continuous. Cosine function continuous. Okay? So, looking through all of these things, you can kind of go through the rest. Continuous. This, on its domain, would be continuous. So these parent functions are all continuous on their domains. Okay? And that's what I want you to understand, is you have to define the domain first before we do anything else. So